Welcome to Module 8 of GenAI from Zero to Hero. In this module, we will learn about agents, why agents matter, how agents work internally, how to build them, and how to control them. Here is our roadmap. We will define an AI agent, explain why it matters, and explain how it works. Then we will explore tools, memory, planning, and multi-agent systems. After that, we will talk about risks and safety guardrails, and we will finish with architecture, debugging, cost control, and where agents are heading. Pause for a second and set your expectation. By the end, you should be able to explain an agent in one sentence and sketch its architecture on paper. This is the entire story in one picture. A traditional prompt is a single turn. You ask, the model answers. No real memory, no iterative work, and no actions in the real world. An agent is different. An agent takes a goal, makes a plan, uses tools, stores what it learns, and repeats this process until the goal is achieved. Example. Prompt. Summarize this article. You get a summary. Agent. Create a 9-day Switzerland itinerary for the elderly and kids with hotel options and travel time. The agent may search, compare, organize, refine, and produce a final actionable plan. An AI agent is not just an LLM. It is a system. Think of it as 4 parts working together. 1. The LLM does reasoning and language. 2. Memory stores context, so the system is not forgetful. 3. Tools allow action, web search, database queries, APIs, code, and calendars. 4. A decision loop keeps the agent moving step by step toward the goal. If any one of these is missing, you might still have something useful, but it becomes less like an agent and more like a smart chatbot. Let's make this painfully clear. A chatbot is usually one input, one output, and mostly stateless. Even if it feels like it remembers, it often depends only on the current chat window. It usually does not execute actions. An agent is multi-step, stateful, tool-using, goal-driven. Here's a simple test. If you can close the chat and come back later, and the system still continues your task with stored state, you are closer to an agent. This flow explains why agents feel more powerful. Chatbot flow. Ask and get an answer. Done. Agent flow. Goal, plan, act, observe, improve, repeat, deliver. That loop is the secret. The loop is why agents can handle tasks that need refinement. Example. Write an email. A chatbot writes one email. An agent can draft, check tone, validate facts, add missing details, and even send it through an email API if allowed. Memorize these components because you will use them to design and debug agents. Goal. What success looks like. Planner. How to break work into steps. LLM engine. Decision-making and language. Tools. Actions in the world. Memory. State and learning. Feedback loop. Adapt based on results. Tip. When an agent fails, the failure usually falls into one of these categories. Either the goal is unclear, the plan is weak, the tool call is wrong, memory is missing, or the feedback loop is not guiding improvement. The goal is not do the thing. The goal must be testable. Bad goal. Find a good hotel. Better goal, find 3 family-friendly hotels in Fuquoc under $200 per night with breakfast, high review scores, and low walking required. Agents perform best when the goal includes constraints, budget, time, safety rules, allowed tools, and a stopping condition. A planner turns a big goal into steps. The simplest plan is a checklist. A more powerful plan is a dependency tree. Step B depends on Step A. Example plan for create a travel itinerary. 1. Identify travel dates and group needs. 2. Gather top attractions. 3. Estimate travel time between locations. 4. Build a day-by-day schedule. 5. Validate pacing for elderly and kids. 6. Produce final itinerary. Tip: many agent failures happen because the planner is missing, so the model jumps to an answer too early. This is the brain, but remember, it is a probabilistic brain. It predicts good next steps. What the LLM does: 1. Interpret the goal. 2. Decide what to do next. 3. Decide which tool to call. 4. Interpret tool results. 5. Revise the plan. Tip: you should never trust an LLM as a tool. The LLM should decide, but tools should execute. Tools are the agent's hands. Without tools, the agent is stuck inside text. With tools, it can search, calculate, run code, access databases, call APIs, create files, and schedule meetings. Example: if the agent needs today's flight prices, the LLM cannot guess. It must use a search tool or travel API. Tip: tools turn agents from smart talkers into smart doers. Memory answers one question: will the agent remember what matters later? If you do not store state, the agent repeats itself, wastes tokens, and loses context. Memory also enables personalization, supports long-running tasks, and enables multi-session work. Tip: do not store everything. Store what changes decisions: user preferences, constraints, previous tool results, partial plans, and confirmed facts. The feedback loop is what keeps the agent honest. After each action, the agent checks: did we move closer to the goal? What did we learn? What should change? This is where evaluation and safety checks live. Example: if a web search result contradicts previous info, the feedback loop should trigger rechecking, not blind acceptance. In an agent loop, there are 6 structured steps: receive goal, generate plan, call tool, observe result, decide next action, iterate. This loop continues until completion criteria are met. If you build agents, this loop becomes your core algorithm. Always enforce max iteration limits. These 6 steps describe the agent loop: receive goal, generate plan, call tool, observe result, decide next, iterate. Pause and notice: the loop is not optional. Without iteration, you are back to single-shot prompting. Tip: put a hard stop rule. For example, maximum 8 iterations, or stop when confidence is high and constraints are met. Tools allow agents to act beyond text. Examples: web search, calculator, code execution, database queries, API calls. Tools connect reasoning to the environment. Without tools, the agent cannot create outcomes. Agents use 2 types of memory: short-term memory, conversation context; working buffer, temporary task state; long-term memory, stored knowledge, user history, preferences, semantic recall. Implementation examples: conversation buffers, vector databases, structured storage systems. Memory allows continuity and personalization. Let's talk about 3 planning approaches. Reactive agent: act step by step without long-term planning. Fast, simple, but limited foresight. Deliberative agent: creates a full plan before execution. Structured and optimized, but rigid. Hybrid agent: plans ahead but adapts dynamically, balances foresight with flexibility. In real-world production systems, hybrid approaches dominate. When designing agents, always match planning style to task complexity. REACT stands for Reason plus Act. The cycle: thought, action, observation, repeat. This structure improves transparency and reduces hallucinations. If debugging agents, inspect reasoning traces. REACT is a practical agent loop. It alternates between reasoning and acting. Cycle: thought, action, observation. Thought: what to do next. Action: call a tool. Observation: read results. Repeat. Why it works: it forces the agent to ground decisions in real results rather than guess. Tip: in real systems, you often hide the thought from users, but you keep it for logs and debugging. The tool calling process. 1. User goal. 2. Agent reasoning. 3. Tool execution. 4. Tool result. 5. Agent decision. The agent selects tools through structured calls, use function schemas, validate parameters, log execution. This prevents tool misuse. A single agent is where one reasoning engine handles everything. This is simple but limited specialization. Whereas in multi-agent system, multiple specialized agents collaborate. Example roles: 1. Research agent, 2. Coding agent, 3. Review agent. Specialization improves scalability. A single agent is simpler. One reasoning engine does everything. A multi-agent system uses specialists. Example team: research agent finds sources, coding agent writes scripts, review agent checks correctness and safety. Why multi-agent systems work: specialization reduces mistakes and speeds up work by parallelism. Tip: use a single agent first. Move to multi-agent when tasks become complex or need quality gates. If we look at the hierarchical structure of a multi-agent system, let's look at this example. Manager agent delegates tasks. Worker agents execute subtasks. Reviewer agent validates output. This mirrors organizational systems. Delegation reduces cognitive overload. This is a classic hierarchy. Manager agent breaks down the task and delegates. Worker agents execute specialized subtasks in parallel. Reviewer agent validates output quality and catches errors. Example: building a blog post pipeline. Manager defines structure and assigns research, outline, SEO, and proofreading. Workers do each part. Reviewer checks factual accuracy, tone, and compliance. Tip: the reviewer agent is your quality firewall. Agents can integrate with email systems, calendars, CRM platforms, business workflows. To implement, you need to work with APIs. Learn and understand REST APIs, secure authentication, restrict permissions. This is enterprise-level integration. Most useful agents will call back-end APIs to complete tasks. This is where agents become powerful and dangerous. With APIs, agents can send emails, book meetings, update CRM, trigger workflows. Example: a meeting agent that reads your availability, proposes slots, sends invites, and updates the calendar. Tip: never allow direct execution for high-risk actions. Use approvals. For example, draft the email, show it to me, then send only after I approve. Some real-world use cases for agents: autonomous research assistant, automated content pipeline, sales follow-up agent, customer support automation, data analysis assistant. Notice the pattern: repeatable cognitive workflows, something that you need to do over and over again every day, simplified and made autonomous by tools. This is agent-scale thinking. These use cases are common today: research assistants, content pipelines, sales follow-up, customer support, and data analysis. The pattern is the same: goal plus tools plus memory plus loop equals outcomes. Tip: start with one narrow workflow. Do not start with a general agent. Narrow agents succeed faster and cost less. Now that you understand agents and what they are, you should also understand the risks. Infinite loops, tool misuse, hallucinated tool calls, cost explosion, security vulnerabilities, autonomy increases risk. Agents require supervision, logic. Here is where, as humans, you need to plan, refine, and govern agents and how they work. Agents introduce 5 major risks. 1. Infinite loops, no progress, repeated actions. 2. Tool misuse, wrong tool or wrong parameters. 3. Hallucinated tool calls, inventing capabilities. 4. Cost explosion, too many iterations and tokens. 5. Security vulnerabilities, data leaks, unauthorized access. Tip: if you want to deploy agents, assume these risks exist by default and design around them. Some guardrails to follow when you design your agent: max iteration limits, tool restrictions, human-in-the-loop approval, output validation, logging and monitoring. Guardrails convert autonomy into controlled intelligence. Guardrails are non-negotiable. Max iterations, hard cap. Tool restrictions, whitelist tools and actions. Human approval, especially for external actions. Output validation, check the result before release. Logging and monitoring, trace everything. Example: if the agent can send emails, the default should be draft only. Sending requires approval. Tip: the safest agent is the one with the fewest permissions needed to do the job. The basic agent architecture is a layered system: interface layer, orchestration layer, reasoning layer, tool layer, memory layer. Modular design enables scalability and debugging. This layer view is how you build clean systems. Interface, user input and output. Orchestration, workflow coordination and routing. Reasoning, LLM decision-making. Tools, external actions. Memory, context storage. Tip: this modular design makes debugging easy. When something breaks, you know where to look. Example: if the agent calls the wrong tool, it is an orchestration or reasoning issue, not a memory issue. Pause for a second. If you understand this, you understand how to build an AI agent. Everything else is architecture around this loop. Let's break it down carefully. An agent is not magic. It is a controlled loop with memory. Here is the minimal logic. Step 1. Define the goal. This must be explicit, not vague, not conversational. For example, generate a research report on electric vehicle trends using current data. That is a goal. Clear goal definition reduces hallucination and improves performance. If you do not define the objective clearly, the agent will wander. Now, step 2. Initialize memory. Memory stores context and observations. In code, this could be a conversation buffer, a list of previous actions, a vector store, or even a simple structured dictionary. Without memory, the agent cannot track progress. Now comes the heart of the system, the loop. While goal is not complete, think. Select tool, execute tool, store observation, repeat. Let's slow this down. First, think. This is the reasoning step. The LLM evaluates: what do I know? What do I need? What should I do next? This is not action yet. This is planning. Second, select tool. The agent chooses the correct external capability. For example, if it needs live data, web search. If it needs math, calculator. If it needs structured retrieval, database query. Tool selection is critical. Poor tool selection causes failure. Third, execute tool. The system calls the function. This is actual execution. The tool returns a result. Fourth, store observation. The result is stored in memory. This step is extremely important. If you do not store observations, the agent will repeat actions. Now we ask, Is the goal achieved? If yes, return final output. If no, loop continues. That is it. That is a minimal agent. Let me show you the pseudocode mentally. Define goal. Initialize memory. While not complete, think. Choose tool, execute, store result, return answer. Notice something powerful. There is no intelligence outside the loop. Autonomy emerges from repetition. Now here is practical advice. Always include a max iteration limit, a stopping condition, a cost cap. Without these, the loop can run forever, and that is how budgets explode. If you want to implement this today, you can build this loop in LangChain AutoGen, OpenAI function calling, or even pure Python. The framework does not matter. The loop matters. And here is the deeper insight. Most people think agents are advanced. They are not. They are structured repetition with reasoning. The complexity comes from scale, not concept. If you understand this slide deeply, you are no longer learning AI tools. You are designing AI systems. And that is a different level. In the next slide, we move from minimal logic to layered architecture. Now the system grows. But this loop remains the core engine. Master the loop. Everything else becomes engineering detail. Let me ask you something. If you had to automate your office work 10 years ago, what would you build? You would write rules. If this happens, do that. If condition A, execute B. If input equals X, output Y. That is traditional automation. Rigid, predictable, deterministic, and it works beautifully until something unexpected happens. That is where automation breaks. Now, look at the screen carefully. Traditional automation has predefined workflows, explicit rules, manual updates. It depends entirely on human-written instructions. If the situation changes, someone has to rewrite the logic. Now, look at the right side of the screen. AI agent autonomy, dynamic decisions, context awareness, goal-driven adaptation, strategy adjustment in real time. This is not rule following, this is reasoning. That single shift, rules to reasoning, is the paradigm shift. Let's simplify this for you. Automation asks, what rule applies here? Autonomy asks, what outcome am I trying to achieve? That is a fundamental difference. Imagine a customer support bot. Traditional automation. If keyword equals refund, send refund template. If keyword equals complaint, escalate. Now imagine an autonomous agent. It reads context, understands urgency, checks user history, queries policy database, determines best action, executes the workflow. No predefined branch for every scenario. It reasons, and that is powerful. But here's the part most people miss. Autonomy does not mean randomness. It still follows a structure. It still operates inside guardrails. It still respects constraints. Autonomy means flexible reasoning within defined boundaries. Think of it like this. Automation is like a vending machine. You press a button, you get a snack. Autonomy is like a personal assistant. You explain the objective, it figures out how to achieve it. Now, here is where this becomes important for you as a builder. If you are designing AI systems, do not hard code every scenario. Design for reasoning. Define goals clearly. Provide tools. Provide memory. Set boundaries. Then let the agent decide how to reach the goal. That is modern AI architecture. And this is why companies are investing heavily in agent systems. Because autonomy reduces human supervision per task. It scales cognitive work. But remember something critical. Autonomy increases responsibility. More reasoning power means more need for monitoring, more need for evaluation, more need for safety controls. So the real shift is not just technological, it is architectural. From if this, then that, to given this goal, What is the best next step? That is a higher form of intelligence. And if you understand this deeply, you understand why agents are the next evolution beyond prompting. Next, we move into frameworks that help you build this autonomy in practice. Now, we stop thinking like rule writers and start thinking like system designers. That is the transition. And that is where serious AI builders operate. Now that you understand how agents work, here's the practical question. Do you build everything from scratch? No. Agent frameworks help you implement the agent loop, reasoning, tool calling, memory, and orchestration without rewriting infrastructure every time. LangChain offers flexible components for tools and memory. AutoGen focuses on multi-agent collaboration. Crew AI models agents as team roles. Semantic kernel integrates well with enterprise systems. But remember this, frameworks organize intelligence, they don't create it. If you understand the core loop, you can use any framework confidently. Master the architecture first, then use frameworks as acceleration, not dependency. Here's the uncomfortable truth. Agents can become expensive very fast. Why? Because every loop consumes tokens. Every tool call adds cost, and iteration multiplies usage. If you don't control it, your smart agent turns into a smart build generator. So, what do? First, set token limits per iteration. Second, cap maximum loops. Third, batch tool calls when possible. Fourth, cache repeated results instead of recomputing. Think like an engineer, not just a builder. Intelligence is powerful. Controlled intelligence is scalable. If you can't measure cost, you can't deploy agents responsibly. Here's something most tutorials won't tell you. Agents fail in strange ways, not because the model is bad, but because the loop behaves unpredictably. Agents think, act, observe, and repeat. If one step misfires, the entire workflow drifts. So how do you debug this? First, inspect reasoning traces. See what the agent thought before acting. Second, log every tool call, parameters, outputs, errors. Third, analyze loop failures. Where did it get stuck? If you can't see inside the loop, you can't fix it. Debugging agents is not guesswork, it's observability. And serious AI builders always build visibility first. Here's the big question. Where is all this going? With research, content, support, and analysis. Useful, powerful. But that's just the beginning. The future isn't one smart assistant. It's networks of agents working together, autonomous companies, self-managing workflows, AI supervisors coordinating other agents, entire ecosystems collaborating across systems. That sounds futuristic, but early versions already exist. Here's what matters for you. The shift is from tools that respond to systems that operate. The builders who understand architecture today will design tomorrow's digital workforce. Agents are not a feature, they are infrastructure, and we are still at the early stage. Let's lock this in. If you remember only one thing from this module, remember this. Prompting gives answers. Agents achieve outcomes. An AI agent is goal-driven. It uses tools, it remembers context, it works in a loop, and it keeps iterating until the objective is complete. That's the shift. From single responses to structured execution, from chat interaction to system design. You now understand the core loop. You understand memory, tools, planning, guardrails, and cost control. That means you're no longer just using AI, you're architecting it. And that is the difference between experimenting with AI and building real-world AI systems. Look at this diagram carefully. This is not just a picture. This is the anatomy of a production-ready agent system. At the center, you see the LLM, the reasoning engine. But notice something important. It is not alone. Above it, goals. On one side, planning. On another, tools. Below, memory. Around it, feedback loops. This is intelligence structured. Goals define direction. Planning breaks complexity into steps. The LLM reasons. Tools execute in the real world. Memory preserves context. Feedback improves performance. And here's the key insight. Remove any one of these and the system weakens. No memory? It forgets. No tools? It cannot act. No feedback? It cannot improve. This diagram represents maturity. You are no longer looking at a chatbot. You are looking at infrastructure. And once you understand how these pieces connect, you stop thinking about prompts and start thinking about systems. That is where serious AI builders operate. Take a moment and think about what you now understand. You've learned what an agent is. You've seen the loop. You understand tools, memory, planning, guardrails, cost control, debugging, and full system architecture. That's not beginner knowledge anymore. But here's the truth. What you've seen so far is the foundation. Module 9 is where things get serious. We move from single agents to advanced orchestration, from simple loops to coordinated systems, from standalone intelligence to multi-agent collaboration, advanced tooling, and deeper control. This is where agents begin to behave like digital teams. If Module 8 taught you the engine, Module 9 will teach you how to build the machine around it. So don't stop here, because understanding agents is powerful, but mastering advanced agents? That's where architecture turns into advantage. Thank you for completing Module 8. Now you can define an agent as LLM plus tools plus memory plus decision loop. Explain the agent loop and why iteration matters. Pick a planning strategy, reactive, deliberative, hybrid. Implement React-style behavior, thought, action, observation. Design safe permissions using guardrails. Sketch a layered architecture and debug failures by component. In next module, we will dive deeper into agents. Till then, goodbye and happy learning.